So before we get into our discussion on conservation of energy, we have to talk about systems. Now, up to this point, you've probably talked about things like isolated systems, closed systems, and open systems. We're going to simplify the terminology a little bit. We're only going to talk about isolated versus non-isolated systems. So an example, and just to make an analogy of this, in an isolated system, let's pretend you and a friend, you're in a locked room, the door never opens, there's no way to get to the outside world. You and your friend, you have a certain amount of money between you. Now you and your friend are free to trade money, and at certain points you may have different amounts of money for each of you, but at the end of the day, the total amount of money in the room does not change. Let's say you started out with $10, your friend starts out with $5, and you decide to loan your friend $2. So then you're down to $8. Your friend now gains $2, and he's at $7. So while the individual has had their amount of money changing, the total amount in the room has not changed. The total is still going to be $15. What we would say in this example is we'd say that the money is conserved. The money can be exchanged between people, but the total amount of money has not changed. When we're dealing with energy, we can have energy transferred between objects, but we'd say that the total energy is not changing. So that is a case where we're dealing with conserved quantity. Now let's say the door opens. So again, the two people here are free to switch money with one another, but we could also have the case where now with the door open, money could leave the room, or maybe if you're really lucky, money enters the room. At this point, we cannot guarantee that the total amount of money in the room is going to be constant. It's free to change because of this outside influence. So in this case, this would be an example of a non-isolated system. And we can also look at energy in that context. It's a little bit more difficult, however. So in this context here, if we're dealing with energy, this would be a case of friction, because friction would be kind of transferring energy out of your system. But what our focus right now is going to be looking at the case of the isolated system. So as I mentioned, we're only dealing with isolated systems for now. In an isolated system, the total energy available, or the mechanical energy, is going to be constant. It will not change, and that's really important. And the reason for that is it just can't leave the system. It can't just up and leave. It's constrained to that system. So what this tells us that the mechanical energy at some time A, it's going to be the same at some time B later. So the mechanical energy at A is going to be equal to the mechanical energy at B. So we could put this in words. We could say within an isolated system, energy may be transferred from one object to another or transformed from one form to another, but it cannot be increased or decreased. So this idea is what we call the principle of conservation of energy. So on the data sheet, this is physics principle number 5. This is probably also one of the most important principles you'll learn in high school physics. It's used significantly in this course and in Physics 30 and in university level physics. So it's a really important thing to nail down, and it also simplifies some problems that we're going to hopefully see in a little bit. Commonly, though, you may see conservation of energy written like this. So you may see this symbol EI equals symbol EF. So this symbol is the Greek letter sigma. It's the uppercase sigma. Basically, what this symbol means, this means add up or sum up. What this is trying to communicate is that the sum of all the initial energies is equal to the sum of all the final energies. So before, and this equal sign, well, this equal sign could be some type of event. You could have a collision, whatnot, but what it's saying is that at some point in time, all of the energies we'd add up all the kinetic energies and all the potential energies. Sometime later, we'd add up all the kinetic energies and all the potential energies. And for us dealing with isolated systems, these things have to be equal. Another way you may see the above written is you may see EKI plus EPI equals EKF plus EPF. So initial kinetic energy plus initial potential equals initial or final kinetic plus final potential. That also works. It's just an expanded form of this. I'm going to use this notation in the course. Another way we can state this, and it's more useful later, especially in Physics 30, we could say that the change in kinetic energy is equal to the negative change in potential, or we could say that the change in potential is equal to the negative change in kinetic. Basically what this is saying is that one form of energy comes at a cost of the other. So if kinetic energy is increasing, it comes at the expense as a decrease in the potential energy, or vice versa. If we have a gain in potential energy, this is going to come at a cost of a decrease in kinetic energy. Now, and that's the main thing with the principle of conservation of energy. So energy cannot be created or destroyed. It can only be transformed between objects. So we have to always be able to account for that. So the big thing here is that mechanical energy does not change. It is going to be constant because we are going to assume the system is isolated.